in our last lecture we had used the JWKB solutions to solve two eigenvalue problems. One was corresponding to the linear harmonic oscillator, and the second was for the linear potential, linearly varying potential with the potential going to infinity at x equal to 0. In both cases we had only one turning point. So, in this lecture we will eventually calculate tunneling probabilities, but before we do that we will solve one more problem in which there will be more than two turning points, and actually there will be four turning points. In fact, one can handle for that sense any number of turning points. One just have to hop from one turning point to the other, look for the approach the other turning points and hop from one to the other. So, we will illustrate this through the calculation of the eigenvalue problem for a double well potential. We will choose, for the sake of simplicity, a symmetric double well potential, so that V of minus x is equal to V of x. And as we tried to explain in our last lecture, at the end of our last lecture, that the wave functions for such a case are either symmetric functions of x or anti-symmetric functions of x. So, our approach will be that if we have a anti-symmetric function of x, we will start with a sine hyperbolic function. If I have a symmetric function of x, we will start with a cos hyperbolic function. So, let us start in the region from minus the, there are the, for if I assume this, so the potential is given by the double hump, and in fact in order to in the ammonia molecule problem one does have a double well like this. So, I want to find out the energy eigenvalues for this double well problem. I assume any value of energy here. So, E is equal to V of x at 4 points. So, there are 4 turning points. So, actually technically speaking we must start with an exponentially decaying solution here, hop here, obtain the solution here, and then look towards the turning point here, hop from here to here, then from here to here, and then you write in terms of two functions sine and cosine, and the coefficient of the cosine term will be 0, because that will lead to an exponentially amplifying solution there. This is the general methodology of using the WKB approximation for solving any eigenvalue problem. But this case is particularly simple. So, we have either symmetric functions of x or anti-symmetric. So, in the region, first we will discuss in this region, and then in this region, and then in this region. So, let me first start with this region. So, you have psi of x. So, this is the first region, let us suppose. First region, psi of x is equal to a by root kappa cos hyperbolic, or again for the anti-symmetric function I can take sine hyperbolic 0 to x kappa of x dx, where kappa of x is equal to under root of 2 mu by h cross square v minus e, because in this region mod x less than a, v is greater than energy, the assumed energy. So, therefore, we must use kappa square of x. So, in order to use the turning so we will have exponential solutions here and trigonometric solutions to the right. So, you must write it in the form of x to a kappa dx, exponential minus and exponential plus. So, therefore, first of all you must write 0. So, this is equal to, first I must write it in terms of the exponentials, 0 e by 2 e to the power of integral 0 to x kappa dx plus e to the power of minus 0 to x kappa dx. And then the trick is that you write 0 to x kappa dx is equal to 0 to a kappa dx minus x to a kappa dx. So, we will write that e to the power of, so let me write this as theta, this as theta. So, the first term becomes a by 2, please see, e to the power of theta, e to the power of theta, e to the power of minus with a 1 over root k outside, x to a kappa dx plus e to the power of minus theta 1 over under root of k, because this is a minus sign here. So, this will be minus here and plus here, e to the power of minus theta e to the power of plus x to a kappa dx. So, now we have solutions, we have written in terms of x to a kappa dx and x to a kappa dx. So, this will, the exponentially decaying solution will go over to a sine solution, exponentially amplifying solution will go over to a cos solution. So, then we will have this goes over to, this goes over to, let me write it down, is equal to a by 2 e to the power of theta, and this will be 2 by root k, that factor 2 you must remember, sine of then a to x k, because in that region x is greater than a, k dx plus pi by 4, and this solution will go over to e to the power of minus theta. I thought I will do this example so that you understand how to use the connection formulae, 1 by root k cos a to x k dx plus pi by 4. So, you see we will have, one is the sine term and the other is this cos term. Now, we have here, so I have obtained the solution in this region. Now, I must write it as integral from x to b, so that I can use the connection formulae to hop from here to there. So, therefore, once again, if this is say phi, so I write phi as integral a to x k dx plus pi by 4. So, I write it as integral, same trick, a to b k dx and then minus integral x to b k dx, and I must add pi by 4 because my correction formula has this pi by 4. So, it is minus pi by 4. So, plus pi by 4 plus pi by 4. So, plus pi by 2. So, let me write this down as this quantity as alpha. So, this becomes sine of alpha plus pi by 2. So, this becomes, so this solution becomes equal to a by 2 e to the power of theta 2 by root k sine of alpha plus pi by 2 minus this. So, that becomes cos of alpha minus this. So, this becomes cos alpha cos of integral x to b k dx plus pi by 4 plus sine alpha sine of x to b k dx plus pi by 4. And then there will be another term. So, when there are more than 2 turning points, the life is in general little complicated. So, you get cos of pi by 2 plus the whole thing. So, that is minus sine. So, this becomes minus e to the power of minus theta 1 over root k 1 over root k. So, sine of alpha minus this thing. So, this will be sine alpha cos of the same quantity x to b k dx plus pi by 4 and then this will be minus sine of a minus b minus cos alpha sine this thing. I hope all of you understand this. Minus cos alpha sine of x to b k dx plus pi by 4. Now, I have now oscillatory solutions here, and now I will go over to exponential solutions here. So, therefore, I must use this, that sine function will go over to an exponentially decaying solution and the cos of x to a will go over to an exponentially amplifying solution. So, this term, please see, this term and this term will go over to an exponentially amplifying solution. So, therefore, the coefficient of those two terms must add up to 0. So, therefore, please see this times cos alpha minus this times sine alpha. This is the coefficient of the cosine term, that must be 0. So, you must have 0 is equal to 2 e to the power of theta cos alpha minus e to the power of minus theta sine alpha. So, you will have the final result as, say, tangent alpha is equal to 2 e to the power of 2 theta. This is the eigenvalue equation that will determine the symmetric eigenvalues of the problem. And I leave it as an exercise for you that if I have the antisymmetric solution, then all that I have to do is I will assume here sine hyperbolic. So, as you know, the sine hyperbolic term will have a minus sign here, and therefore, it will have a minus sign there, and so on. The analysis will be almost similar, except that there is a minus sign here. So, you will get a similar result, but so we have been able to obtain the results of a double well potential, and in fact, one of the potentials that is of great importance in many areas is a double well potential given by half mu omega square x minus d whole square. And the results that you obtain by using WKB and the exact results in terms of confluent hypergeometric functions, they agree quite well with the result, with the exact results. So, in general, if you have a potential looking like this, let us suppose, and if you assume this as the energy level, then the corresponding k square of x will look like this. So, because that will be, these are the turning points. So, you have to start with an exponentially decaying solution here, hop over 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 here, and so on. So, this is the methodology for example, if this was not symmetric, then there will be exponential solutions here, which will go over to oscillatory solution here. Then you look towards this turning point and you go over to the exponential solution here. Then you look towards this turning point. Then you get oscillatory solutions here. Then you look towards this turning point, and then you go over. It is a fairly straightforward procedure, and but it does become a bit cumbersome if you have more than 3 or 4 wells. But in principle, for any potential, you can solve the Schrodinger equation and obtain the eigenvalues. Now, what I will do next is what I had promised on the very first slide, that use of connection formulae to calculate tunneling probability. This is also an extremely important problem in not only in quantum mechanics, but in solid state theory and thermionic emission and things like that. And we had discussed one simple potential, and we discussed the tunneling, made a tunneling calculation, that we had a potential like this, and we assumed V to be less than V0, V can be greater than V0 also. So, in general, one considers E less than V0, and then we have a incident wave here and a reflected wave here, and then we assumed only a transmitted wave here. So, here the solutions was A into e to the power of ikx plus B into e to the power of minus ikx. The first term represents a wave propagating in the plus x direction. The second term represents a wave propagating in the minus x direction. Why? Because the time dependence is of the form of minus I e t by h cross, which is equal to e to the power of minus I omega t. So, you have a incident wave incident on this potential step potential, and then there is a reflected wave. But there is a transmitted wave here, and there cannot be any wave propagating in this direction, because there is no reflector here. There is no reflector here. So, you assume a solution, we had assumed a solution of the form of f into e to the power of ikx, and in this region we had written down the solution as c into e to the power of kappa x plus d into e to the power of minus kappa x. Then we applied continuity conditions at x is equal to 0 and at x is equal to a, and found out what was f by a whole square. This is the tunneling probability, and what was B by A whole square, this was the reflection probability. But this is a step potential, it is an idealized situation, and in general you have a potential variation like this. And here the solution of the differential equation becomes extremely difficult. So, if you have a potential like this, if a particle like that is, if a particle is incident with a certain energy E, then there is a certain probability of it getting tunneled through the barrier, and what we would like to do is to calculate the tunneling probability using WKB result. So, if this is the V of x variation, this is the V of x variation, and the point at which E is equal to V of x, these are, as I had mentioned earlier, these are the classical turning points A and B. Why is it a turning point? If I, for example, if I have a mountain in front of me and I throw a tennis ball, then the ball will climb up the mountain to a certain height and will come back. To what height will it climb? It will climb to a height so that the ball comes at rest, and therefore that is the point at which the tennis ball turns back. So, that is, those are the turning points. So, that is why they are known as turning points. Similarly, we had considered the harmonic oscillator point. The harmonic the pendulum makes an oscillation like this. At the extreme point, the displacement is given by x is equal to, say, x0 cos omega t. X0 is the amplitude, and at that point the total energy is potential and the kinetic energy is 0, and the particle turns back. So, in the case of the linear harmonic oscillator problem, the plus minus x naught or plus minus a are the turning points, are known as the classical turning points of the problem. So, here you have the turning point. So, what we are planning to do is that this is the potential energy variation, this is the potential energy variation V of x as a function of x, and here is a particle of energy E which is incident from the left on the potential. So, I want to solve the Schrodinger equation d2 psi by dx square plus 2 mu by h cross square E minus V of x psi of x. This is my k square of x. Is equal to 0. So, if I plot k square of x, then it will look like this. These are the points at which k square of x is 0, and these are the classical turning points at which the particle will turn back. Our approach will be like this. What we will start out with is there is only an outgoing wave in region 3. So, this is region 1, this is region 2, which is the classically forbidden region. This is the classically forbidden region, because the potential energy exceeds the total energy. So, classically a particle cannot tunnel through the barrier, and this is the region where there is an outgoing plane wave. So, we will assume in this region psi of 3 a plane wave. Now, plane wave will be of the form of e to the power of I k x. So, we will write an outgoing plane wave, we will write as, say, f, the WKB solution will be root k, because k is positive here, k square is positive here, root k e to the power of I integral x k dx. I will put the lower limit as b so that I can, it helps us in using the connection formulae, and also put a phase factor pi by 4, because you remember that in the connection formula there is a, in the correction formulae there is a phase factor of pi by 4. So, I will write the solution in the region 3 in this region as psi 3 is equal to so much. Okay. So, in the region x greater than b, in the region x greater than b, therefore, we have the solution f by root k. So, we rewrite it now in terms of the third region, we write it as f by root k in terms of the cos and the sine function. So, you will have cos of b to x k dx plus pi by 4 plus I sine integral b to x k dx plus pi by 4. Okay. Now we, this is the solution in this region for x greater than b. I want to hop over the turning point and come to the region x less than b. So, the sine solution will go to an exponentially decaying solution, and the cos solution will go over to an exponentially amplifying solution, and we will be using this particular. So, the sine solution will, we must remember to put the factor of 2 correctly. So, this 2 will come here and this cos solution will go over to 1. So, this will be equal to f over root of kappa. Now, E is less than V of x, and so you will have e to the power of x to b kappa dx plus I by 2, there should be a factor of 2, e to the power of minus x to b kappa dx. So, this is the solution in the second region, where x lies between a and b. So, therefore, it is from x to a. So, this is x to b, because b is my turning point, b is the turning point here. So, the integrals have to be x is less than b. So, it is a x to b. Now, we have the solution in this region. We have to now go over to the first region. So, we have to look towards the turning point A and write integrals in terms of a to x. So, therefore, let me write it down that x to b kappa dx we will write as integral a to b kappa dx minus a to x kappa dx. Since this is e to the power of this, so we define a symbol which is theta, which is defined to be equal to e to the power of minus integral a to b kappa of x dx. This is the definition of theta, which we must remember. So, therefore, the function in the region second will be f over root k, this is e to the power of a to b kappa dx. So, that is 1 over theta integral e to the power of minus integral a to x kappa dx plus I theta by 2, because there is a minus sign here. So, this will be e to the power of minus a to b kappa dx, and then e to the power of plus a to x kappa dx. Now, we have here, therefore, we have now the oscillatory solutions are the exponential solutions are to the right, the oscillatory solutions are to the left. So, now we will use once again the connection formulae to go over to region 1. So, this will go over to, we just have to do patiently, psi 1 of x, this is the WKB solution using the connection formulae. So, I am sorry, this should be kappa, because in this region k square is negative. So, this will be f by under root of k now, because in region 1 k square of x is positive. So, the exponentially decaying solution will go over to 1 over theta 2 sine of let me write it down as alpha. I will write down what is alpha, plus I theta by 2 cos alpha. And what is alpha? As you all know, this will be integral x to a k of x dx plus pi by 4. Okay. So, this I have now obtained the solution in terms of sine and cosine functions. Now, we must express the sine and the cosine functions in terms of the exponentials, so that we know which one represents the wave propagating to the right and which one propagating to the left. So, this becomes equal to f by root k 1 over theta sine alpha, that is e to the power of I alpha minus e to the power of minus I alpha divided by 2I. So, 2 cancels out with here. So, it becomes I plus I theta by 4 now, because cos alpha will be e to the power of I alpha plus e to the power of minus I alpha. That is it. So, if I take out I here, so I will get I f by, let me do it in 2 steps, I f by root k, although this is trivial. So, this will become minus 1 over theta e to the power of I alpha minus e to the power of minus I alpha. I have taken outside, so theta by 4 e to the power of I alpha plus e to the power of minus I alpha. So, this becomes e to the power of I f by root k. So, the e to the power of I alpha will be theta by 4 minus 1 over theta into e to the power of I alpha, and then theta by 4 plus 1 over theta, that is e to the power of minus I alpha. Now, so I hope this is clear. Now, we notice that what is alpha? Alpha, as we wrote down, alpha was equal to integral x to a k dx plus pi by 4. So, e to the power of I alpha, of course, there is a phase factor e to the power of I pi by 4. So, this will be x to a k dx plus pi by 4. Of course, there is a pi by 4 there, but that is immaterial. What I want to tell you is that if k was constant, then this will be e to the power of minus I kx. So, e to the power of alpha represents a wave propagating in the minus x direction, because if k was constant, since x appears in the denominator in the lower limit, so this will be minus I kx. Of course, there is an a also. So, x minus a actually, but that is a constant factor. I do not worry about that. But the x dependence is of the form of minus I kx. So, this represents a wave propagating in the minus x direction. Similarly, e to the power of minus I alpha is a wave propagating in the plus x direction. And so, therefore, this is the coefficient of the wave propagating, this is corresponding to the reflected wave, and this is the incident wave. And I have the coefficient of the, so the coefficient of the, so the coefficient of the, so the reflection coefficient of the transmitted wave f. So, this is the coefficient of the transmitted wave, this is the incident wave, and this is the reflected wave. So, that the transmission coefficient will be 1 over theta by 4 plus 1 over theta whole square, and the reflection coefficient will be this reflected amplitude, that is theta by 4 minus 1 by theta whole square divided by the coefficient of the incident wave. So, that is theta by 4 plus 1 by theta whole square. The amazing thing is that in spite of all the approximations that we have made, the sum, the T plus R is equal to 1. Now, we had seen that theta we had defined as equal to e to the power of minus a to b kappa dx, kappa of x dx, and therefore, this quantity is usually less than 1. So, therefore, the in this expression for the transmission coefficient, T is equal to, if you add, I left as an exercise for you to show that T plus R is equal to 1. So, T will be, this term will be very small compared to this term, because 1 over theta will be, so I can neglect the theta by 4. So, this will approximately become 1 by 1 over theta square. So, this is equal to theta square, and this is equal to e to the power of minus 2a to b kappa of x dx. Thus, we have calculated the probability of tunneling as a particle approaches a potential barrier. So, we had started out with a potential barrier which looked something like this. It is a smoothly varying potential and a particle of energy E is incident from the left. So, E is equal to V of x at these 2 points. So, these are the 2 turning points which we denote by A and B, and we found that the tunneling probability is equal to exponential of minus g, where g is equal to 2 integral a to b kappa of x dx. In the region A to B, the potential energy is greater than the total energy. So, it is a classically forbidden region, and so therefore, the expression for kappa is 2 is equal to 2 under root of 2 mu by h cross square integral v of x minus e under the root multiplied by dx, and the integral is taken from one turning point to the other. So, this is a very important result, that the tunneling probability in many problems, as we will discuss only 2-3 applications of this in our lectures, but this is a formula which is extensively used at many places. So, let me consider first a parabolic potential. Now, in a parabolic potential, the potential energy variation is 0 in this region, and at x is equal to minus d, this is the x axis, and this is my v of x. So, this is a parabola, and the particle of incident energy E is incident from the left. So, we write down that v of x is equal to 0 for x mod x greater than d, mod x greater than d. So, at plus d also, beyond that the potential energy is 0, and beyond this point, and between, for x less than 0, x less than d, v 0 1 minus x square by d square. This is for x less than d. So, at x is equal to 0, the potential energy is v 0. So, let me calculate first the integral. So, the turning points are, for a given value of the energy, let us suppose that the turning points are given by x is equal to plus minus b, because this is a symmetric potential. So, this will be one turning point and this will be one turning point. So, let this distance, let this coordinate be minus b and plus b. So, at x is equal to plus minus b, E minus v of x must be 0. That is, these are the definitions of the turning points. So, E is equal to v of x, that is v 0 1 minus b square by d square. So, if I take v 0 below, So, therefore, we will get B square is equal to D square times 1 minus E by V 0. This quantity is less than 1 because E is less than V 0. So, this is positive. So, the turning points are B is equal the turning points are B is equal to, therefore, plus minus D under root of 1 minus V 0. The turning points are actually at plus B or minus B, where B is equal to D into under root of 1 minus E by V 0. So, let me calculate the tunneling probability. First of all, we will calculate from the integral from one turning point to the other, kappa of x. This is the first example that we are considering. So, A to B, so this will be from actually A is equal to minus B to plus B, 2 mu by h cross square under root V of x, that is V 0 1 minus x square by d square, x square by d square minus E. So, I take V 0 outside. So, I get 2 mu V 0 by h cross square, and therefore, I get 1 minus, and I take also square root of d square outside. So, 1 over d. So, I will get minus b to plus b under root of b square minus x square times dx. So, at the turning point, the integrand is 0. The integrand is 0. So, this is actually 2 times integral 0 to b. So, therefore, let me then do the same kind of an algebra as we had done before. X is equal to, let us suppose, b sin theta. So, dx is equal to b cos theta d theta, and b square minus, so this becomes, so let me write it on the left, under root of 2 mu v 0 by h cross square 1 over d multiplied by 2, because I will put this integral as from 0 to b. When x is 0, then theta is 0, and when x is b, then theta is pi by 2. So, b square minus b square sin square theta under the root is b cos theta and b cos theta. So, therefore, this is b square cos square theta d theta. The integral is really trivial. So, b square we have already shown before that b square was equal to d square into 1 minus e by v 0. Okay. So, we will write down. So, b square is equal to, so I take b square outside. So, we will get 2 times b square, that is d square 1 minus e by v 0 multiplied by 1 plus cos 2 theta by 2, 1 plus cos 2 theta by 2, integral from 0 to pi by 2. The second integral will be 0 as we had shown out earlier. So, the first integral will be half into pi by 2. So, therefore, so 1d cancels out with 1d. I can take d inside. So, I will get under root of 2 mu v 0 d square by h cross square. This is a dimensionless number multiplied by 1 minus E by V 0, and so there is a 2 factor. So, this factor 2 cancels out with this factor, and this will become, the integral of this will simply become pi by 2. So, this integral, as we had just now shown, was equal to a to b kappa of dx, and the tunneling probability is equal to e to the power of minus g. So, g is equal to 2 integral a to b kappa dx, kappa of x dx, and this will be 2 into pi by 2 will be pi under root of 2 mu v 0 d square by h cross square into 1 minus e by v 0. Okay. So, this is just one example. So, we have just solved the problem. So, this we write as example 1, and this is just to give you an idea as to how you use the tunneling probability formula, which we had used by using the JWKB approximation. You first find out the turning points, and then you integrate kappa of x dx from the first turning point to the second turning point, and you will get the expression for the tunneling probability. Now, then we next consider a very important, a very simple problem, but very important problem in solid state physics, namely cold emission of electrons. That is, that inside the metal, let us suppose you have metal, and inside the metal there are free electrons, and let us suppose at t equal to 0, at absolute 0, as all of you know, all the levels up to the Fermi level, say at t is equal to 0, the Fermi level, say in sodium or potassium, is around few electron volts. We had discussed that when we considered the free electron theory of metals. Now, then there is a work function, that the electrons inside the metal experiences a work function, that it requires a certain amount of energy to go outside the barrier, to go outside the metal. Now, what we do is, I put an electric field here, so that the potential energy variation is something like this. So, therefore, the electron here at this energy sees a very high, or near the Fermi level, sees a very high potential, and so therefore, it classically it cannot go to the other side, because in this region the kinetic energy will become negative. But quantum mechanically it is possible for the particle to tunnel through, and so therefore, if you have a metal surface and you put an electric field, then even at very low temperatures, where all the electrons are below the Fermi level, there is a certain probability that the electrons will tunnel out. Let me calculate this probability. So, we consider this case where you have what is known as a triangular barrier. So, we consider, just as we considered the parabolic barrier. So, let me consider example 2 as the triangular barrier. So, this is my x axis, and this is the potential energy variation. So, I have 0 here, and let us suppose this point is there. So, the potential energy variation V of x is equal to 0 for x less than 0, and this is V 0 minus alpha x, V 0 minus alpha x for 0 less than x less than a. This is the potential energy function, and then it is, we assume it to be 0 for x greater than A. Actually, this goes to infinity, but we, for the sake of simplicity, we assume that this to be. So, in this region it is linear. So, what we will next consider is that in the next lecture we will assume a particle to be incident of a certain energy E, and for the given energy we will calculate the first turning point will be at 0 and the second turning point will be here, and we will calculate the WKB tunneling, JWKB tunneling probability, and from that we will try to derive an expression for thermionic current, that is known as the Fowler-Mod-09 cold emission formula, and it is completely a quantum mechanical phenomenon, and it is a manifestation of the tunneling of electrons through a potential barrier. So, we leave right now here and we will proceed from this point onwards in our next lecture. Thank you.